So today I wanted to look at writing my own Hexdump program. Now the default Hexdump program in Linux is XXD, and so if we look at the man page for XXD, it tells us that it creates a hex dump of a given file or standard input, and it also has a bunch of these different flags. So Hexdump is great for looking at the hexadecimal values of binary files, so you can kind of take a look at their contents because you can't. It's not very good to print out a binary file, but you can also print out hex textual files as well. So XXD, the way that I use it is I normally have, one or two flags that I'm using it with. So you can use it with just a file itself and get a hex dump of an entire file. But you can also get, use the L flag, which is length, and get print out a certain number of bytes. You can also have an S flag, which will give you an offset. So if we choose an offset of 1, then that means that we'll start at an offset of 1 and then print out the number of bytes that you want. And you can see the format of this dump is to print out the address of the bytes, the starting address that you're for that line. And then 16 bytes, if it is that long, 16 bytes in 2-byte groups, and then a textual representation of that line, if it is possible. If there are bytes in there that cannot be represented graphically, then they are represented by a dot or period. And so that is essentially Hexdump or XXD. So I want to create my own version of this that just has the features that I use, and as kind of a didactic version. So what I did is actually I accidentally have a file in here. There we go. So what I did is I wrote this ahead of time because I wanted to essentially cut out the time for me typing all of this up. So I wrote this and I just want to go through it. The one thing I want to tell about before we start is that I made some minor changes to our macro that we created previously. I just changed the variable names or the parameter names of this getArg function. Because we're passing argc and argv into it, I just wanted to use those variable names. It makes it a little bit more readable, and that's essentially the only change I had for that. So let's take a look at the program itself. So let's see, vim. So we'll take a look at the bottom here with the main function, and we'll see that we use our macro that we created previously, and I have two flags here, the L flag to get the max length and the O flag to get the offset. And then of course, if we give a flag that doesn't exist, we'll just print out the usage and exit. One thing to note is that I didn't do any error handling here. So if the user types in something that's not a number or something that's bad, then you'll just get a bad answer out of this. If it's just possibly a 0. So it's kind of up to the user to give it a proper number. The other thing is after we've dealt with our flags, we have regular arguments. So if we have one argument, we're going to assume that it's a file and dump out that file. Otherwise, if there are 0 arguments, we're going to dump from standard input. Otherwise, we'll give a usage. So if someone tries to dump 2 files, it's not designed for that, and it will just give a usage statement. Okay, so the two main functions here are dump file and dump stood in. So let's take a look at those. So dump stood in just calls dump file descriptor with the file descriptor 0, which is standard input. Dump file opens a file using the open system call and gets a file descriptor. If we get a bad file descriptor, then we have an error. Otherwise, we dump that file descriptor and close the file descriptor. This is nice because we treat standard in and dump file as the same thing. If we go up to the top here, we have the usage, which is just printing a single line telling the user how to use the program. And then this is the meat of the program. So this dump file descriptor or dump FD. The idea behind it is that we just create a static or we create a fixed size buffer, which we're just calling buff. And the idea is we're going to read into that buffer, one buffer chunk at a time. And then once we've got that, we're going to loop inside of that buffer and write one 16-byte chunk at a time from the buffer. And we'll just keep looping through all of this until we dump the entire file. So that's the strategy behind this. And so we're going to take a look. This is exactly what we do. The first thing that, of course, that we want to do is seek to the offset that if we give an offset. So normally, if there was no offset given, it will be 0. So we'll just seek to 0. Then we do this big loop that I talked about. So we read buff size into the buffer. And then in gives us the number of bytes that we read into the buffer. And of course, we will continue reading these chunks as long as we've read something and we're less than the maximum length. Then there's some bookkeeping operations that we have to do. So for example, we've got to clamp the in value. So if we read a chunk from the file, and let's say that we've already read some chunks or the max length that we have is less than the total number of bytes in the file, then we want to clamp in. We want to say, hey, the number of bytes that we actually want to read from this buffer is going to be smaller. So that's exactly what we do here. Then we create a position variable, which is essentially our position inside of that buffer. So as we loop through that buffer, position will keep track of where we are inside the buffer. So then we'll just loop through the buffer. And so we'll just loop through the buffer and write one line out of that buffer at a time. And of course, our line is going to be 16 bytes if we can. The written variable keeps track of how many characters that we've written to a line. The limit variable tells us how long our line should be. Now, normally that will be 16, but if our in value, right, if the number of bytes that we have to write is less than 16, then we need to clamp this line value to whatever that number is less than 16, and that's what this does. Okay, so now that we've got bookkeeping out of the way, we can write our actual line. And the first thing that we've got to do is write the address. And so that's exactly what we do. Then we have essentially two loops that we want to do. The first loop is to write the part of the line that is hexadecimal. And that's exactly what happens here. And there's a little bit of bookkeeping that puts a space in between those because we want to write in 2-byte groups. Of course, we grab a character from the buffer and then write it in hexadecimal, and then we keep track of where we are. So after we've written that part of the line, then we print out essentially some spacers, right? So we want to write some spaces, and the way that we calculate this is that we have a fixed size for a line, right? So if we want to write a line out, there is the number of bytes for this line, which is going to be 8 plus the colon plus the space. And then, of course, the 16 characters plus all the space, the 16 bytes, which will be 32 bytes, plus the spaces in between them. So all of that turns out to be 41 minus the number of written spaces. So if we've written less than 32 bytes for 32 characters for this part, right? Because our line could be shorter. We want to write some extra spaces. So this gives us all those spaces that we need to write. And then finally, for the last part, we write the textual representation. And so what we do is we just check if this byte is a graphical character. If it is, we just write it as a character, an ASCII character. Otherwise, we just print out a dot. And then, of course, we have some last bookkeeping operations. We're going to write a new line because we've written a line. And then we keep track of our total, our address, and then the position that we are within our within our buffer. And that's it. That's Hexdump. It's actually quite a small program. If we count the number of lines, it's just 79 lines of C, which is very tiny. And we can go ahead and run it now. So what I did is I wrote this little build script, which is just a single line that uses GCC to compile with optimization 3, and then it calls the binary HD. So if we run that, it will build the HD executable, which is only, 16 kilobytes. And then we can try running it. So if we do HD with short flags, it gives us exactly what we expect out of this. And we can compare it with XXD. So it should look exactly the same, except there is no syntax highlighting. And that's exactly what we see, which is nice. The other thing that we can do is we can run our program and try out the flags. So if we say print out 78 bytes, that should be the first 78 bytes. The other thing that we can do is try out the offset flag, which let's say 12 bytes, and that will offset that will start at an offset of 12 bytes and then print out 78 bytes, and we see that it does that. So it has all of the features that we need and want from Hexdump. So that's nice. Now, the only thing left that we probably want to try out is to see how fast is this? What is the performance? All that we did is a very straightforward representation, so we expect HD to be slower than XXD, but we kind of wonder, how much slower is it? So I have a program, a little utility I wrote called TimeIt, which actually runs a program multiple times and gets some statistics from it. So we'll run XXD, and we'll run it on a program that I already have. So I have a slide presentation program called Zent. So we'll run this, and we'll see how long it takes. And it looks like the average time was 210 milliseconds approximately. So we'll run our HD program. We're expecting it to take longer, and it looks like it does. But in a few seconds, it should print out how long it took. So it looks like the average time for a run was 557 milliseconds. So we see that our program is about, just over 2 times slower than the optimized C program. And who knows, there may be assembly or something in there. I haven't seen the source code for XXD, but I assume it's going to be much larger in order to have all the optimizations. But if you think about it, that's not bad at all. We actually wrote a very straightforward version of the XXD utility, and we did it in an extraordinarily small amount of lines, 79 lines of C, and it's a great learning experience. So I just wanted to give this as an example to you that, hey, it's worth trying this out. Maybe write your own utilities. Is there some utility that you use all the time? Maybe cat or ls? Maybe write your own version of this, and you can learn a lot about the operating system that you're running on, the libraries that are available. Say for C, you can see all the libraries that exist. For example, I think there's a readdir library or function. And so if you want to write ls, write your own version of ls, well, you can learn how to use readdir. And that's a very great learning experience. So I would very much encourage that, because none of this is magic, and you can just figure it out and do it yourself. And it's a wonderful experience. So that's about it for today. And until next time.